Now that we know how much data we need to scale for, let's see which database solution works best for us. The database needs to handle 200,000 reads and writes per second, where each update is on average 100 bytes, and total storage we need is 3.6 petabytes. So let's start with thinking on the lines of relational database like MySQL. MySQL will be great for high consistency that we need. And with master replica architecture, we can get great availability as well. However, will we be able to scale the single node MySQL for 3.6 petabytes? Furthermore, every time a user sends a message, we'll have to update a row in the DB. So every second, we'll have to update 200,000 rows on average. This is really inefficient for our system and does not scale well. So MySQL may not be appropriate for our use case. Next, we could think on the lines of NoSQL like MongoDB. Mongo will suffer the same problem that MySQL did for large updates every second. However, because of Mongo's sharding and horizontal scalability, that can be improved to a great extent. Furthermore, Mongo will be able to scale to store 3.6 petabytes with horizontal scalability. However, the problem is the replication delay between the shards, which will increase the latency and also sacrifice strict consistency of data. For these reasons, Mongo also may not be able to serve our purpose efficiently. Since the major problem we are facing is updating the DB for each message sent, Apache HBase is meant to solve exactly that purpose. Instead of updating DB, it will store and group the messages in a buffer, and when the buffer gets full, it will bump the data on disk. It is also meant to scale with a lot of data and provides enough flexibility for varying message sizes. It is also well optimized to store and read smaller data much faster. For these reasons, HBase seems like a good fit for our use case. To store images, a more ideal solution could be Azure Blob Storage since it is well optimized for images. Now, just storing messages in HBase is not the end of our solution. Our app's efficiency will depend on how we structure data in the storage. Dumping all the chats in a single hierarchy will really hinder the app's performance. So let's try to approach the problem in two ways for now. First, we can solve for private chats and then for group chats. In private chat, how about we simply use user IDs as a partition key? User ID A will be first partition and user ID B can be the second partition. Inside this, the chats can be stored in a sequentially retrievable and compressed format like Parquet files. The problem with this structure is that for 3.2 billion users over the next 5 years, this approach will create 3.2 billion partition buckets. This could be a bottleneck for our application while retrieving the messages, since the retrieval will scan keys of all these buckets. So we need a way to limit these buckets. What if we could do something on the lines of hashing? If we can sort the user IDs to always have a deterministic value and then apply a hash function on them, it will always give a consistent hash key. We can limit the number of buckets by modding with the maximum number of buckets. Now let's see how many data shards do we need to handle the data. Let's assume 1 TB shard is roughly 4 TBs. So to store 3.6 petabytes, we will need about 900 shards. So perhaps we can apply the hash function and mod it by 900 to determine which shard would a user's data belong to. To balance out the shards, we can further combine this approach with consistent hashing. A third approach we can think of is perhaps what if we use message IDs as the partition keys. The problem here is with billions and billions of messages over the years, this will create way too many partitioning keys for our application to work properly. So we can certainly not use this approach. Now, coming to group chats, we can perhaps do a similar thing here by hashing each group ID to determine the correct bucket for that group's data.